Hello, year 10s. So we are going to start P7, and the first topic is about energy stores, and then we'll be moving on to efficiency. So the first topic for today would be energy stores. So as per the specification, what are you supposed to know? Describe different situations where the energy transfers take place. Recall the law of conservation of energy that you have already studied in your lower classes, and then all the changes that is involved in a way energy is stored when system changes for common situations. So what you have to keep in mind here is we are going to talk about the energy stores, which is slightly different from the energy transfers we have been or you are more used to from your previous years. So we are going to concentrate on what are the ways in which the energy stored is changing from our next slide onwards. So as I just said, the key term that you'll be using in the beginning of P7 is energy stores. So till now, once upon a time when you did all those energy, different types of energies, what you had done so far is the energy changes from, say, kinetic energy to potential energy. You haven't used the word stores. So now onwards, you have to use, or in most of the questions, you have to use the word stores. So what does that mean? It is energy store represents the energy an object possesses. In other terms, it is the energy that can be stored. You can't store all the energies. So it is the energy that can be stored. So which are those energies? Now, let's go into a bit more details of the different stores of energy. So the chemical energy, it is the food you eat, a chemical reaction that is happening. For example, you can see coal burning with oxygen, the glucose in your muscles. So all those are examples of chemical energy. Thermal energy, of course, all of you know, anything that is a source of thermal radiations or heat radiations or hot bath. Kinetic, anything that is moving is going to have a kinetic energy. Gravitational potential energy, anything that is at a height from the ground will have gravitational potential energy. Elastic, anything that can stretch will have elastic potential energy. Nuclear, so the two main sources we have is nuclear fission and fusion. So uranium and then fusion happening in the sun. Electrostatic whenever it has to do with charges, and magnetic whenever it has to do with the poles of a magnet. So for some of them you have studied equations already, some of them no. For example, chemical energy, there is no particular equation for you to calculate it as such. Thermal energy is the one you have studied in P1 already, related to the specific heat capacity. Kinetic, gravitational potential energy, elastic potential energy, all those equations you have already studied in P2. Half mv square for kinetic energy, mgh for gravitational potential energy, then half kx square for elastic potential energy. Nuclear, you have not studied it. You have not studied it yet, but it is a very famous Einstein's equation of E equals delta mc square. Electrostatic and magnetic, even though here it says none, there are equations to find them, but they are a bit complicated, and you will come across that. You will get the privilege of studying them once you take physics for A levels, okay? Then, so you can, what is the order for you to remember this? Cement kg is something you can use to remember the order: C chemical, E elastic, M magnetic, E again electrostatic, N nuclear, T thermal, K kinetic, G gravitational. Now, when you remember, when you look at this order, you might be thinking, so which are the energies that is not there in this that we have come across before? Can you think about any other energy you think you have studied before, but it is not mentioned in the list here? Can anybody think about something? It starts with S, energy transfers you have studied before. When a collision takes place, what will the kinetic energy change to? You will definitely hear a sound, isn't it? So we used to say it gets transferred into sound energy, but you can see sound is not there in this list. Electrical energy is not there in this list. So whenever they talk about the changes in the energy store, please make sure we don't mention sound or electrical. So as you can see in that yellow box here, store is a very important key term for exams. If you just say energy is transferred from chemical energy to kinetic energy, you won't get marks. You have to say energy from the chemical store is transferred to the energy in the kinetic store. Okay. So as I said, you have already come across conservation of energy. So what does conservation of energy generally mean? Conservation of energy generally means that when one store empties, another energy store is being filled up somewhere. So we said when energy, so the one you have studied so far is energy is transferred from one form to another, isn't it? So in terms of energy stores, when one energy store is emptying, another energy store is filling up somewhere. So basically it is exactly the same thing that you have studied before. Energy cannot be used up, it is conserved. It can be used in a different form, it can be wasted, but it is never destroyed. And as usual, energy is measured in joules. Okay, is that okay, all of you? So from there, we are moving on to how can the energy be transferred. So we have already we already very clearly know that energy can be transferred. So far we said from one form to another. So now we are rephrasing it as energy can be transferred between different energy stores. Okay, so it can be transferred from different energy stores. In which ways can it be transferred? We are interested in the three main ways in which it can be transferred. One, as you can see, mechanically. That is where you are applying a force. You are moving something. So that is a mechanical transfer of energy. Electrically. So using electric current, you are doing some energy transfer there. And third one is by heating. That heating can be by heating the particles directly or by heating by radiation. So the three ways in which generally energy is transferred from one store to another. I'm just emphasizing the importance of the word store there. So the three ways in which energy can be transferred from one store to another is 1. Mechanically, 2. Electrically, and 3. By heating. Now all these have equations related to them, and you have come across all these equations before itself. So mechanically means, as I said, you have to apply a force. So how much is the work done or energy transferred mechanically? When you applied a force, what distance did it move? So force times distance. Just recently, when you studied P3, current electricity, you came across energy transferred there as power times time. And you had studied three equations for power, I square R, VI, and V square over R. Remember? So power times time means I square RT, VIT, or V square over RT. And the last one is by heating. Heating, this is the equation you have studied in your P1 unit. So if you're you're trying to change the energy or transfer the energy between the stores using heating, then mass times specific heat capacity times change in temperature is the equation you will use. It becomes more clear and it becomes more easy to understand when you're doing questions related to this one. Okay, so let's look at an example now. So I have a ball in my hand, okay, and I'm going to throw that ball up. So what are the energy transfers that is going to happen? So as soon as the ball leaves my hand, it's going to have, I'm going to apply a force on it. So it's going to have maximum speed. So it will have some kinetic energy because it is having a speed. It is at some minimum height from the ground. So it will have some gravitational potential energy, but not much. So you can see the kinetic store, the gravitational store. So, and then it will have, everything will have always thermal energy. So its thermal energy store also has some energy in it. Then the ball starts to go up. As the ball is going up, what is happening? What will happen to the speed of the ball? The speed of the ball keeps decreasing, isn't it? And at the maximum height, what will happen? The ball comes to a stop. So at that maximum height, when the ball is stopping, will it have any kinetic energy? No, because the speed is 0 means kinetic energy has to be 0. That is why if you look, you can see the kinetic energy store has become empty. And then again, it is at the maximum height from the ground compared to the height initially. So what will happen to its gravitational energy store? It will increase. So look at this one and look at this one. You can see the difference there. Okay. And then obviously work is being done. So its thermal energy store also increases. So what is the energy transfer that has taken place here? You can see that initially there was energy in the kinetic store. So the energy from the kinetic store has moved to the energy in the gravitational store and the thermal store. So energy has been transferred from the kinetic store of the ball to its gravitational store and thermal store. Initially, previously, we would have just said kinetic energy of the ball has been transferred to the gravitational potential energy and thermal energy. So here, instead of that, energy from the kinetic store has been transferred to the gravitational store and thermal store. So can you see the difference in how we are approaching the same situation? Okay, now let's see another example. So you can see a picture of a man trying to push a huge rock up a mountain. So let's see how the start point when he's at the bottom of the mountain and the end point when he's on the top of the mountain, they are going to differ. So at the bottom of the mountain, so he has lots of chemical energy, okay, and the gravitational potential energy is also there slightly. The person has thermal energy and the surroundings also has thermal energy. So then say he pushes the rock all the way up to the top of the mountain. Can you see what has happened to his chemical energy store? His chemical energy store decreases, so it has come down. His gravitational, there's a spelling mistake here. His gravitational energy store has increased, and then his thermal energy store, because he's doing work, has increased. Energy is dissipated to the surroundings, so the thermal energy store of the surroundings will also increase. Now, so by the end, you can see by the time he reaches the top, he might be, if he's really tired, he would have used up all his chemical energy store. But then you can see whatever has been the decrease in the chemical energy store, it would go out as the increase in the gravitational potential energy store, increase in the thermal store of the person, and increase in the thermal store of the surroundings. So no energy will get destroyed. All the energy get transferred from one energy store to the other. Okay. So these are the things you need to know about the energy stores. I don't know if you think it is a bit confusing. Actually, there is nothing to be confused about it. All the energy transfers that you have studied so far, we are just adding another word to it. Instead of chemical energy store. That is what they are looking for. The key thing is to remember that those two energies which you used to use before as a transfer, which is electrical energy and sound energy, whenever they ask you about the changes happening in the energy stores, you would not mention sound energy or electrical energy. Other than that, everything else is how you have studied before. So instead of saying it gets transferred from kinetic energy to gravitational potential energy, we would say the kinetic energy store decreases and the gravitational potential energy store increases. That's only main difference there. When you do, there are questions in your blue booklet and yellow booklet. So when you do those questions, it would become more clear. So now we are moving on to energy efficiency. So how efficient is an object? For example, when we are using an electric bulb, we switch on the bulb for light, right? Nobody switches on a bulb on a cold evening, on a winter evening, thinking I need to get some heat from the bulb. But whenever you switch on the bulb, you will be definitely getting thermal energy also from it. But that is not the purpose of the bulb. So what is the useful thing we are getting from it? What is being wasted from it? How much is being wasted from it? All these things determine how efficient something is. So we are giving them some work to do, and then how much is wasted from that? How much is being transformed usefully from that? Those are the things that decides how efficient it is. So we have two equations that comes with it. Again, these two equations you have to add to your list of 20 plus equations that you have to memorize. One equation is in terms of energy, and the other equation is in terms of power. Both are the same equation itself. The only thing you have to keep in mind is if you're using energy, you should be using energy both in the numerator and denominator. If you're using power, use power both again in the numerator and denominator. So there are two equations to figure out efficiency: useful energy output by total energy input, or useful power output by total power output. Now, when you're using these two equations, you will be getting your answer as a decimal. Then if you want, you can multiply it by 100 and write it as a percentage. Okay, but what you need to keep in mind is efficiency will be never greater than 1, or it will never be greater than 100%. So when you get that 100% after you're multiplying with by 100. So whenever you're doing any calculations and you're getting the efficiency as before you multiply it with 100, you're getting the efficiency as 1.78, or you're after multiplying it with 100, you're getting the efficiency as 200%. Then you don't even have to think twice. 200%, you have gone wrong there. Okay, so then when you're getting a number greater than 1 before you multiply with 100, or after multiplying with 100, if you're getting a number greater than 100%, then go back, check your calculations. There should be something wrong somewhere. Okay, so these are the two equations. Now I'm going to give you a couple of minutes to write the equation down, and I know most of you would have been writing when I was talking about it itself, but if somebody was listening carefully without writing, it is your chance to write the equations down now. Now let's do some practice questions. The first few questions is just worded questions. So you have a light bulb. So what type of energy are you giving to it? So here they are not talking about stores. So don't worry anything about the stores here. What type of energy are you giving to it? That is all you have to say here. Input energy for a light is electrical energy. What do we want from it? We want light energy from it. But as I said before, we get heat energy. So the wasted energy is heat energy, but I would prefer to write that as thermal energy. Okay, then electric drill. So it's there in the name itself. Electric drill, what is the input energy there? Electrical. It moves. So when something is moving, what is the energy that comes from it? Yes, kinetic. Then again, we are not using drill for, definitely the drill gets a bit warm after we use it. We are not using it for heat. How do we always come to know that we are using the drill? It produces a sound. So the wasted energy there is sound and thermal. Then TV, again electrical energy. When we are watching TV, we need to hear what they are saying and we need to see what is happening. So light and sound. But as I said before, if you check, the TV becomes warm after some time. So thermal energy is the wasted energy there. Car, it runs on fuel. We are not talking about the recent electric cars we are having. So fuel it is. So it has to be, which is the energy associated with fuel. It starts with a C. Yes, chemical energy. Cars we use here to move from one place to another, right? So that is kinetic. Again, it will produce sound. It will produce thermal energy. Okay. So these are the changes in energy taking place. Now, to make your life easier, when they want you to do the changes between the energy stores, most of the time they would not give you something that's it is working with electrical energy, because then it is difficult for you to, in your level, it is difficult for you to say what are the changes happening there. Okay, so whenever it is they want you to write it in terms of energy stores, they will be giving you something that has chemical in it in the beginning, or kinetic or gravitational, something like that, to make your life easy. Okay, now we will move on to the mathematical questions with this one. So let's start with the mathematical questions. So you already know how particular I am with all the data and stuff. So an electric drill uses a total of 160 joules. So that is the energy. Joules means they are talking about energy. That is the energy given to it. So that is the input energy. Produces 90 joules of kinetic energy. So electric drill we are using for movement like we saw in the previous slide. So that is our useful energy. And then it transfers 70 joules of energy to the thermal store. Do we use drill for thermal energy? We don't. So that is our wasted energy. So what does our equation say? Efficiency is useful over total input energy. So useful is how much in the question here? 90. You're giving it totally 160. So 90 divided by 160. How much is it? 0.56. So this is 0.56, or if you want to write it as a percentage, you can write it as 56%. Okay? Then the next one. It is already telling us that the efficiency is 25%, which means if I want to put it in the equation, efficiency is 0.25. How much energy, how much input energy is, so what I have to find, produces 100 joules of useful energy. So if I go back to the equation, efficiency is useful over input energy, useful energy over input energy. What do I want to find here? Input. So I have to rearrange the equation. You have to be careful with the rearrangement. So efficiency times the input, I'm taking input to this side, is equal to useful. And what do I want? I want input. So I'm leaving input there. So input is useful divided by the efficiency. I'm bringing efficiency to this side. It was multiplication. When it comes to the other side, it becomes division. So how much is my input? Useful was 100. Efficiency is 25%. So 100 divided by 0.25. Remember to make it into decimal before you put it in the equation. And the answer is 400 joules. So my input is 400 joules. Okay. And the last question, efficiency of 40%. So that is 0.4. How much useful energy is produced from 250? So this is our input energy. Going back to the equation, efficiency equals useful energy over input energy. I don't have space to write on my screen. That is why I'm limiting it to useful over input. In the exam, when you are writing it, make sure you say useful energy over input energy. So what I want to find is useful. So I'm taking input to the other side. Efficiency times input is equal to useful. So what is efficiency here? 0.4. Input is 250. So useful is 0.4 times 250, and that is equal to 100. So this is a very easy topic. The only thing you have to be careful is rearranging, especially when you have to find the input energy. Now all these three questions are given in terms of energy. It doesn't always have to be on energy. It can be in terms of power also. Okay. This video is available in our non-physics, non-such world of physics YouTube page. So anytime you feel like you need to go back to it, you can go back to the video there. Okay. Now you can proceed with the questions in our blue booklet and yellow booklet.